Now is the lightning talks.
Hello, everyone. My name is Hadi Aghayi. I am a PhD researcher under the supervision of Dr. Christian Deppen, Dr. and Professor Roger Boche. And this is a joint work with Dr. Christian Deppen, Professor Boche, network oblivious transfer via noisy channels, a quantum leap. So we studied the feasibility of oblivious transfer via non-signaling assisted noisy channels, and we considered multiple access channel. Before everything, I have to point out that the usefulness of non-signaling correlations over multiple access channels is studied already by Fauzi and Fermi. They have shown that if we share tripartite non-signaling correlations between Alice 1 and Alice 2 and Bob as two senders and one receiver, we can improve the sum capacity of a noisy multiple access channel. So in this problem, we considered oblivious transfer as a cryptographic primitive. And oblivious transfer is complete, meaning that if oblivious transfer is possible between two parties, then they can use oblivious transfer as a black box to compute any secure function. And this is very nice. In this problem, we have considered two senders and one receiver. Alice 1 and Alice 2 want to send two messages separately and obliviously to Bob, and Bob is only allowed to choose one of them and should be unaware of the unselected string. And from the sender side, Alice should be unaware of the selected string. So this is a two-party secure computation. The first figure is the oblivious transfer system model over multiple access channel with two encoders and one decoder. And in the subfigure C, we have substituted the encoder and decoder box with a tripartite non-signaling box. And we have shown that oblivious transfer is not possible in this case because Bob is also included in the correlation. And in subfigure B, we have substituted the bipartite non-signaling correlation with only encoders. So we shared non-signaling, bipartite non-signaling correlation only between the transmitters. And in this case, we can have oblivious transfer. And the next open question would be that how much we can benefit from this non-signaling correlation to increase oblivious transfer capacity. So for the first discussion, please come to my poster and we can discuss.
Hello everyone, my name is Igor Bernard. I'm doing a PhD on quantum information theory under the supervision of Professor Arun Padakandla in Eurocom. And I will present my poster on instrument simulation. So a measurement produces two objects, an outcome and a post-measurement state. What we call a quantum instrument simply specify this post-measurement state. Our goal here is to simulate the following action: to perform a measurement and send the outcome to a receiver. So this induces a communication cost in terms of classical bits. And the question is, how can we reduce this communication rate? So one quite interesting point about it is that adding an extra resource, some common randomness between the encoder and the decoder, helps to reduce the rate. You can see it as a third person rolling a dice and giving the result to both the encoder and the decoder. That enables them to coordinate. So one point I like to highlight is that preserving the post-measurement state is crucial because one might want to employ some other protocols on this post-measurement state, like some purity distillation or entanglement distillation protocols. So then we study this problem in the distributed setting, which means that the input state is a bipartite state, which is split between two encoders spatially separated with two distinct communication links. And furthermore, we study this problem in the one-shot setting, and we give some achievability rates in terms of R1, R2, the communication rates, and C1, C2, the common neuronal rates. And in the one-shot setting, which means with the finite length input states. And that's it. Thank you.
Okay, so this poster is on integrated sensing communication with rate-limited helpers, and there we want to characterize exactly this trade-off that was already asked. So we have the monostatic setting. And the new thing is that we have a feedback encoder, which sends feedback back to the estimator, and also a state helper or a state encoder, a helper, which sends some information about the state to the encoder. What we try to understand is exactly the trade-off between the distortion level, the rate of communication, and the two feedback rates. So we have two feedback rates from state estimator and from the feedback channel. And that's the thing that we want to understand. Okay, that's already everything. So, yeah. So the first poster was joint work with Tobias Oechtering and Michael Skoglund from the KTH and Ichi Chen. And the plan was that Ichi Chen will present this poster, but yeah. Okay, so the next thing is complete characterization of the arithmetic complexity of capacity Gaussian fading channels. So Gaussian fading channels are the most simplest channels that we know. They are even in standard textbooks like C and Viswanath. So we know the capacity, but we don't know coding schemes achieving this capacity. And I was always interested to understand why is coding so hard, and proving capacity results much easier than coding. So in a capacity, if we prove a capacity theorem, then of course what we do is we use some techniques to show the existence of codes, good codes, and then we compute the rate of these codes and they converge to capacity. So here everything is known for this fast fading channels. The capacity is a very simple expression. And now I'm asking, okay, why is it so hard to construct coding schemes? And the answer is very simple. Actually, it's not possible to construct a capacity achieving code. So what we did is we constructed fading statistics which are computable L1 norm. Everything is computable. You can put this in the computer, but at the end the capacity is a non-computable number, and we even specified exactly the degree of non-computability of this number. And the funny thing is, it belongs to the first hierarchy, and it can be shown that you can have an effective achievability part, which means you can find a sequence of achievable rate that converges from below, of course, to the capacity, but the converse is never effective for this type of channels. So you can never have so for these channels, you can never have a computable sequence of converse bounds which converge to the capacity. Yeah, and that's why, of course, if the number is not computable, then you cannot control the achievability. And that's also an example where you cannot control the finite block length performance of this channel. For DMCs, everything is simple, but even for this very simple channel, if you have to do something with this flower, it's not possible. Okay, that's my, yeah, good. So that's my third poster, yeah, and yeah, actually, yeah. So that's a joint work with Vince Poor. It was also planned that Vince will come here to Braunschweig, but he was not able to move. So I have to present this. So what I want to show is that convexification of a non-convex optimization is in general not Turing computable. So it's a very simple question. So you have an optimization problem. The optimization problem is not convex, but maybe you are able to compute the biggest convex minorand of this function, and then just optimize this function. And then at the end, of course, we know that the optimizers of these functions, the convex set of these optimizers on the function on the right side, the optimizers on the left side are part of this. So we can somehow recompute this. And of course, computer science is the science of automated problem solving. So you can only do this in an automated way if you are able to compute the convex minorand, but that's exactly what we show, that this is not possible. So you can you can find very simple computable function, infinitely often differentiable, such that the convex optimization or the convex minorand is not computable. And that is also related to information theory, because in information theory, we always have to compute, not always, but very often, the convex hull of sets of the rate region. And this is also not Turing computable. So you can find convex rate regions such that the convex hull is not Turing-computable.
If you pay attention to Neha's talk yesterday, then you should know what a Bizant mic is. And if for all of you who doesn't attend Neha's talk yesterday, it's a network where adversarial user is the hidden, but you don't know which one is the adversarial one. And the original problem in classical is already difficult, but in quantum we face many new difficult problems. Thank you. And just to present one of them is that not only the channel noise can destroy the message, but if you, for example, first decode the adversarial's message, then you can destroy the message by the decoding operator. So this shows that the quantum network is much sensitive to uncertainty.
Hi, I go by Guy. It's easier for everyone. And I'm a PhD student at HHU Düsseldorf in the group of Dagmar Bruce. My project is on the security of supernancy coding under polynoise. So this is a quantum communication protocol. And in our version, we start with, we have Eve, the eavesdropper, and we have two trusted parties, Alice and Bob. And we have the eavesdropper distribute our initial state. And we're also interested in noise. So this is sort of noisy supernancy coding. So to represent that, we have an initial state where with 1 minus lambda probability, Eve distributes basically the state as normal between Alice and Bob, and then she has a Q-trit flag, and with probability lambda, that's our noise parameter, she distributes instead the state between Alice and herself. Then Alice encodes the message directly by Pauline unitaries, so identity XZ, XZ. Then Alice sends her qubit to Bob and performs a Bell measurement. Our quantity of interest is chi, or the Halevo quantity, which basically is a measure of the information between two of the parties. And if you look at the graph here, the blue is between Alice and Bob, and you can see that it decreases kind of as expected as the noise increases. And the yellow is between Alice and Eve, and so it increases as the noise increases, which is expected because the noise is due to Eve. However, what is interesting is that by utilizing this Q-trit flag, Eve is actually able to gain more information about Alice's message than one would expect. Thank you.
Okay, hi, my name is Christian Eckrich. I'm from TU Darmstadt, and my poster is about distributed radar sensor networks under communication constraints. So on the left side, you can see some radars, and they are observing two persons. And you can also see that there's one radar that has a blocked line of sight to the targets. So, but therefore we have distributed sensing, because in distributed sensing, you have multiple diverse viewpoints, and you can increase accuracy and coverage. But in order to leverage those advantages, you have to move the transmit your radar data to a centralized fusion center. And there you do joint estimation. But as you scale the network, this communication part here seen in blue becomes the bottleneck. So therefore, in order to mitigate this, we have to move our communication resources to those sensors which are most informative. And this is our problem then. We want to minimize the localization uncertainty for sensing, but we want to, under the constraint that we satisfy the rate capacity posed by the network, the rate capacity constraint posed by the network. Now, in order to satisfy this constraint, on my poster, I will present two approaches. The first one uses quantization, and there we utilize rate distortion theory in order to map some achievable rate to some distortion noise. And the second approach would be sensor selection. We are selecting which sensor is transmitting or reporting about which target, and therefore lose some information. So the key takeaway from my poster is that if we want to design a distributed radar sensor network, we have to take communication constraints into account. And this is especially important if we have limited communication budgets. Thank you very much.
Hello, everyone. My name is Ramuzin, and I'm a doctoral researcher at the Technical University of Munich under the supervision of Professor Holger Bocher. And the poster I present today is about common random misgeneration from sources with infinite Polish alphabet aided by unidirectional communication. And this is a joint work with Wafala Bidi, Moritz Wiese, Christian Zepper, and Professor Holger Bocher. So as you may know, in the problem of common random misgeneration, we have multiple communicating parties who aim to agree on a shared random variable with high probability, and this is under limited communication. And common randomness is considered as a highly relevant resource in many applications, including secret key generation, misidentification, and modular coding schemes. Now, in our work, we're interested in the two-source model for common randomness generation with one-way communication, with a particular focus on sources defined on infinite Polish alphabets and on one-way communication over noisy memoryless channels. And the goal is to study the common randomness capacity for this model. The common randomness capacity is defined as the maximum achievable common randomness rate. Now, our results are as follows. First, we'll establish a single letter bounds on the common randomness capacity for the general setting. And as an example of sources defined on infinite Polish alphabets, we will consider Gaussian sources. And for the case of Gaussian sources, we will establish a closed formula for the common randomness capacity. And we will show in particular that when the Gaussian sources are perfectly correlated, then the common randomness capacity is infinite. Last but not least, we will highlight the fundamental contrast in common randomness capacity between finite and Gaussian sources, showing that moving from finite to infinite alphabets leads to a fundamentally different behavior. So I hope to see you at my poster to have further discussions about this topic. Thank you.
Hello, everyone. I'm Vida Golamian from Technical University of Braunschweig. Actually, I wanted to present our joint work with Dr. Deppe, Professor Bocher, and Professor Scheffer. First of all, I wanted to mention most important difference from identification and transmission. Actually, in identification, we wanted to just know in receiver side the message was sent or not. We didn't need to know whole of the message. Our system model is Alice wanted to send the message to Bob in presence of the wiretapper. We have the feedback from the channel and sensing in Alice side, and the state is unknown for both of receivers and sender. And at the end, we will prove that if the Shannon secure capacity if be positive, so the OR system models channel randomized identification capacity, it could be equal to output, maximum output entropy under constraint of sensing, under sensing constraint, sorry. Thank you. And I would be really happy to see you on poster session. Thank you.
Hello, everyone. Sorry. Hello. So my name is Fatma Gbia. I'm a PhD student at ULCOM, and I'm working with Professor Arun Padakandla. So today we will present a poster on information theoretic study over quantum multi-terminal channels. So my work focuses on communicating classical bits over quantum interference and quantum broadcast channel. Specifically, 3-user quantum interference channel and 3-user quantum broadcast channel. And we aim to characterize the achievable rate region of the capacity region of these two channels. So, so in these settings, each receiver sees a bivariant interference. And our goal is to design an efficient coding scheme to that exploit the structure of coset codes to decode the bivariant interference, and thereby derive new inner bounds that subsums all the current known inner bounds and that are strictly larger than the for some identified examples. We also employ CNA's recent technique called tilting, smoothing, and augmentation to enable simultaneous decoding of coset codes.
Hello, everyone. Unfortunately, Paul is not able to make it in person due to illness yet to travel to Spain for medical treatment, so I have to do it. This poster is the result of a joint work together with Chris Aaron Schneider and Christian Deppe, which started around 1 year ago and finalized last autumn, when it was presented in the European Wireless Conference 2025. In the poster, you will find a new protocol for key distribution that falls into the subclass of hybrid key growing, and it incorporates several novelties compared to the two dynamic schemes. These novelties include the two you can see in the slide. The first one, we proposed to use a photon number, also called Fock state encoding, and this is motivated us to rely on so-called coherence witnessing for detection. This first novelty turned out to be undesirable, if taking into consideration the state of the art in Fock state manipulation. This is why we see in red. Our second novelty instead turned out to be more fruitful. What we propose is to achieve authentication. Grantees with quantum channels is opposed to the standard choice of doing it via the classical one. This idea had already been explored in the literature, but our approach differs from all previous ones and has opened promising new lines of investigation in currently ongoing projects. Being the nomination, one of the topics of interest for this conference, the main message that this poster aims to convey is that coming up with new ideas is important, as well as is it to tell between those that are promising and those that should be discarded. In this process, bad ideas may be a necessary starting point to reach good ones. Thank you.
So hello, my name is Rodrigo. I'm a new PhD student in the University of Braunschweig. I'm here just to present a poster about what my PhD is going to be about. So I've been here just for 3 weeks, so this is really fresh to me. And my supervisor from the university is Christian Deppe, and my supervisor, because my PhD is also in collaboration with TISAT. So my supervisor from TISAT is Julian Struck. And the motivation for this PhD is the possibility to build a satellite network for worldwide quantum key distribution coverage. So the idea is to not using discrete variable quantum key distribution, and the reason for this is that the difficulties to implement these kind of protocols, but we are aiming to use a continuous variable quantum key distribution. And to do this, we are going to first, we want to address this, say, problem first by doing an analysis between only 2 satellites. So this would be the most simple model. And we will study the different protocols, the security proof, and also one of the biggest challenges, which would be the Doppler shift. And if everything goes right, then we would scale up into thinking about building a network and some of other considerations like a dynamic or a static constellation. So that's it.
Hello, everyone. This is a joint work with Hadi, Christian, Edward, Marcel, and Holger. So in this work, we are considering a 1 out of 2 oblivious transfer. So in the model, Alice will transmit 2 messages, and Bob will choose one of them. And we need to design a protocol to avoid Alice knows which one will be chosen by Bob. And meanwhile, we need to avoid Bob to know the unchosen message. In this work, we propose to use a polar code to implement this protocol, and we propose this system model. Yeah, if you have interest, please come to my poster. I will explain it to you. Thank you. Here is Carol's slide, which is about security of optical key distribution against quantum-enhanced coherent eavesdropping. So in the talk given by Conrad, so they proposed this optical key distribution scheme, and they found that the secure against most powerful quantum passive eavesdropping is possible. So in this poster, Carol will explain to you how this key distribution can be implemented by a specific way. Thank you.
Yeah, my name is Marcel. Vida has already introduced what is identification via channels, so I don't need to introduce that. Just briefly speaking, my poster is about second order coding rates for identification via channels. So we look at the deviation from channel capacity. How does the rate converge towards capacity? We want to find the second order coding rates. And specifically, we are looking at the scenario of identification with noiseless feedback, which has some interesting properties. For example, the capacity has a very weird behavior that it gets larger when we have more noise in the channel. And so we were interested, what does the second order coding rate look like? How do we approach capacity? And when you want to know what it looks like, come to my poster.
I'm Kumar Nilesh. I'm a PhD student at TUM under Professor Holger Bokeh. So when you look at future of 6G network or massive IoT networks, there is a big threat at user identification that Mark was pointing out this morning before lunch. So in this poster, I will talk about the user identification, especially from the classical side, why the classical biometric-based system or classical device fingerprinting fails, and how with machine learning and enough data, you can clone classical fingerprints or classical physically unclonable functions, and how quantum biometric or feature extraction gives you a better alternative. But when you move from one-to-one authentication to one-to-many identification, you face something called a resource quadrilemma, where any system designer needs to have a trade-off or balance between the competing resources. We will talk about 4 such competing resources, and in our poster and later in our paper, we have characterized these resource trade-off information theoretically that can help any system designer to design their system where this would either focus on scalability or security. And yeah, we will discuss what are the applications of these quantum biometric-based feature extractions are. So you're welcome to visit my poster. Thank you.
Hi, everyone. I'm Nikita. I'm a PhD researcher from TU Dresden. I'm working in the group of Riccardo Basoli. I'll be presenting my recent papers, communicating properties of quantum states over classical wireless channels in the poster session. Okay, so I work in quantum semantic communication. The main motivation of this idea is basically coming from the semantic communication, and more especially from the goal-oriented communication or task-oriented communication. So basically in task-oriented communication, the essence of a communication task is, let's say, between the two parties, transmitter and receiver. The receiver is more interested in understanding or recovering the properties of the task more rather than let's say reading the whole data itself. So in this protocol, what we do is we provide a new solution using shadow tomography based transmission with unequal error correction with unequal error protection, where we go one step beyond the state of the art, which uses quantum shadow tomography to extract the classical properties, or let's say classical data, from a quantum information. So in this approach, what I do is especially we develop shadow tomography, where using the shadow tomography, use fewer measurements to generate the properties of interest and then communicate these properties of interest to the receiver, who is just interested in certain observable finite length observables over the full data itself. The more details I'll be sharing in my poster session. You're all welcome to join. Thank you.
Hi, I'm Claire. I'm from the Quantum Information Group in Hanover. I'm a PhD student there, and my poster is on Pinsker type bounds for quantum divergences. So we have already encountered quantum divergences in some of the talks, and I will explain to you what Pinsker type bounds are in a minute. So imagine in some information theoretic task, you come up a quantum divergence, for example, this one. This is the standard relative entropy. And it may be hard to compute. So you wonder, well, can I express it in terms of quantity that is easier to compute, for example, the trace distance? And the question now is, okay, how are D and T related? The first thing we know is that the relative entropies are always positive, and the trace distance is between 0 and 1. So we know that we look at this region. If you now pick your two favorite quantum states and you calculate D and T, you will get a point in this graph. For example, this one. You can do it for 10 more points. You can do it 5,000 more times. And then you see, well, we don't have a one-to-one correspondence between D and T, but we still have hope to find some relation between the two, because we have some kind of region that looks like it has a lower bound. So our goal is to find the optimal lower bound, so a function of T that for any two quantum states I get, D is always greater than this function of T. And these bounds are called Pinsker type bounds because Pinsker's bound does exactly this. And you can see this is a quadratic function in T, but it's not optimal close to 1. And we rather would want to find these optimal bounds. And in our work, we do exactly this. We find optimal bounds for any quantum divergence you can imagine, and it turns out that it's actually quite simple using a two-step method, and I will explain to you how it works when you come to my poster.
Yes, I am Moritz from Technical University of Munich, and I will present a poster made mainly by a PhD student I co-supervise, Johannes Feuchtleitner, and he did experiments to as efficiently as, well, to efficiently validate semantic security in wiretap channels. So this is on information theoretic security. And we try to do what, well, we try to approximate the best possible eavesdropper attack, which is or not unfeasible, which is very inefficient. We try to make this a bit more efficient to get actual empirical bounds on the security performance of an eavesdropper. Thanks. For details, yeah, come to my post.
Hello, everyone. My name is Hussein Notour. I'm a PhD student at the Quantum Communication Group of Professor Ziperek from Technion. Today, I'm going to present a joint work with my colleague Gabriel Lalou and with Uzi about quantum secret sharing rates. So the quantum secret sharing is a very important cryptographic primitive in which we have the idea is that we have a certain dealer the dealer has a certain quantum state that he would like to share to some parties, where he sends some partial information about this secret to each one of the parties, and only if a certain subset of these parties collaborate to interpret the secret and decode it, then they can do this. So for example, in this setting, we have a dealer that creates a certain quantum state, which is a qubit in this case, psi, and he sends a certain quantum particle to each one of the parties, Alice, Bob, and Charlie. And in this case, only two subsets of two or more can decode the secret. So for example, if Alice and Bob collaborate together, then they can, using this scheme of CGL, Cleve, Gutzman, and Liu, they can do the reconstruction of the secret by doing these two steps, by collaborating with each other. And this is not exclusive only for Alice and Bob. For example, if Alice and Charlie collaborate, then they can do the decoding as well, but then Bob has no access to the secret. So in our work, what we do is that we study quantum secret sharing in the case where the channel used for transferring the encoded information from the dealer to the parties is actually a noisy quantum channel, which makes the analysis a bit more challenging. And we derive the achievable rate region. So I'll be very glad to get your questions in the post session, and thank you.
Okay, hi everyone, I'm Junshen from TU Braunschweig. In my poster, we are presenting a multiple access channel. So we have a lot of transmitter in this system, and they want to transmit to the same receiver at the same time. And since we are interested in the system where we have a lot of transmitter, so we believe that it is difficult to synchronize all the transmitter with each other. So we consider the asynchronous multiple access channel. And as you can see, we have many encoder, many transmitters, and each transmitter has an individual delay to transmit to the receiver. And since now they are asynchronous, so the transmitted code word are not aligned to each other. So now we are interested in the latency constraint. So for some application, maybe these transmitted messages are urgent to be decoded. So the receiver want to decode at the nth channel use. And for some application, maybe we can wait a little bit longer until the receiver receive the complete transmitted code word and then decode the messages. And in addition to these properties, we also found some very interesting differences in our error analysis between the synchronous case and the asynchronous case. So if you are interested in the multiple access channel or the asynchronous case, or you are curious about what is the interesting difference between synchronous and asynchronous case, then you can come to my poster and we can have a more detailed discussion.
So hello everybody, my name is Lorenzo Taniboni and I'm a PhD student at the Technical University of Munich under Professor Kramer. And this is a joint work with Professor Mark Flanagan from University College Dublin. So we consider a single user monostatic radar scenario with a near field constraint. That means that the distance between the base station and the user equipment is smaller than the so-called Rayleigh distance. So given this constraint, we have to take really into account that the near field channels, they depend both on angle and distance, which are the two parameters that we try to estimate. In order to do it, we decided to use uniform circular arrays that are, in this case, more suitable for the spherical wavefront, which are characteristic for the near field communication. So our goals / contribution are, in this case, to consider a continuous time system model with respect to the fact that the majority of the literature is considered discrete, that takes into account the delay and the Doppler shift. And also, we want to see which are the performances of the UCA-based estimation in near-field system. So since it is like an early stage, we have early stage result, I would be happy to have a very nice constructive talks at my poster. Thank you.
So hello everyone, my name is Yang. I'm from Christian Deeper's group. And today my poster is about joint identification and sensing with noisy feedback. So it refers to the problem that we want to do the identification, and at the same time we want to estimate the channel state. So my colleague Marcel and Vida already talked about a lot about identification with feedback, but here we consider the noisy feedback is more practical assumption. So So you can see here we consider strict causal noisy feedback Z instead of the noiseless feedback Y. So in our work, we established a upper and lower bound for the capacity distortion trade-off, and for both deterministic and randomness encoding scheme. And this is particularly difficult for identification because we, in this case, the randomness, the feedback and the channel output is not naturally common. So if you're interested in this topic and want to know this in details, I'm happy to discuss with you in the poster session. Thank you.